Thank you, Killian. Welcome, everybody. I hope you're ready for an action-packed presentation. Okay, a little bit about me. So I was born in Trinidad and Tobago. You may not know where that is. If you're a sports fan, you may know it as the birthplace of Brian Lara and Dwight York. If you're a history buff, you may know it as the place where Francisco de Orellana got stuck for 3 days after emerging from the Amazon in 1542. Since none of that probably helped, it's close to Barbados. Okay. So like Killian said, my background is in civil engineering and petroleum engineering, and hilariously, neither of those career paths worked out for me. So now I do this. Within the 20 years or so experience that Killian talked about, I have 14 years within process safety management in oil and gas, petrochemicals, and nuclear energy. I'm currently working with FDT, now NIRIS, as its process safety lead, where I support clients with their process safety management services, which really means it's a lot of HAZOPs. This is going to be a silky smooth kind of presentation. So we're going to look at the origins of inherently safer design, where it fits in risk management, what the principles are. We're going to look at some real world experiences where maybe inherently safer design could have made a difference in the design of process systems. And we're going to look at some methods for actually incorporating inherently safer design into a project. I realize it's a lot of young people here, but if you've worked in the industry for a while, have you heard of inherently safer design? Just raise your hand. Okay. Have you applied inherently safer design to a design project? Okay. And put up your hands if you've applied it consistently through all phases of a project and documented it in detail to allow an auditable trail. Okay, there you go. That looks about right, yeah. Okay, so just to start off, an event that didn't go so well and maybe inherently safer design could have made a difference. So October 31st, 2014, a reusable suborbital rocket for a space tourism company owned by a billionaire, which you may know about, was undergoing a flight test. So the design of this vehicle used two twin booms, which they call feather flap assemblies, and those stayed at a 0-degree angle in normal flight. During re-entry, the feather flap assemblies would be rotated to 60 degrees to stabilize the vehicle and to slow it down as it re-entered the atmosphere. The protocol for these feather flap assemblies is that they had to be unlocked at Mach 1.4 during the ascent. And the concern was that you got up into space and the locks would not disengage, and now you've got a serious problem on your hands. So in this test, the co-pilots unlocked the feather flap assemblies at transonic speed, which was 0.8 Mach at this point. At transonic speed, you have a lot more stresses on the vehicle. Those stresses overcame the actuators on the feather flaps. The feather flaps deployed, and the extra drag on the vehicle tore the vehicle apart, killing one of the crew. So unlocking the feather flap assembly is a fairly straightforward process. It's basically just pulling a lever from lock to unlock, but it's an extremely difficult environment to do it in. So for one thing, there's time pressure. The co-pilot has 3 seconds to unlock the feather flap assembly. After 3 seconds, computer will start screaming at you. And at 1.6 Mach, the flight would have to be aborted if they have not been unlocked. And at that point, you have a bunch of people who have paid $500,000 mad at you because they have not made it into space. It's a very difficult operational environment. You had vibration and G loads. So the video from the cockpit recording showed the co-pilot had to lean off of his chair in order to reach the lock. His head was bouncing around. He was having a lot of problems getting a good hold on the lock. Also, the co-pilot was not used to the conditions. So he had qualified fully on a simulator, but this was his first actual flight in the spacecraft. The unlocking steps are listed on a kneeboard, but pilots had said that there's so much workload in that environment that there's no time to actually look at those steps, and you're doing it all from memory. And the company assumed that pilots would get it right all the time because they had been trained. I'm not a rocket surgeon, so I'm not going to speculate on what the correct answer is. But based on the difficult working conditions and the fact that you could kill somebody if you get it wrong, that was an ideal time to think about how could we possibly do this differently. And maybe inherently safer design could have made a difference there. Okay, ISD's origin. So there was a guy named Trevor Klett, and he is the OG of ISD. So in the 70s, there were a whole bunch of fairly bad industrial disasters. And in 1978, Trevor Klett thought that something had to change, and he actually formalized the idea of inherently safer design. So his thing was that if you don't have something, it can't leak. And that has the added benefit of making your plant simpler, cheaper to operate, easier to maintain. The thing is, since humans started actually doing stuff, we've been applying principles of inherently safer design, even if you don't know it. I mean, we're all here because our ancestors applied inherently safer design on some level in order to survive. So, for instance, say you're in the desert southwest of the United States 800 years ago, and you're part of the Anasazi tribe, also known as ancestral Pueblans. You got other tribes that are raiding you all the time, taking your stuff, killing your people, and you got a number of options for handling that. You got to do something about it. So maybe you can raise an army, but then you have to train these people, you have to develop weapons, all of that takes resources. So why do that when you can just take all your stuff and just move it up a cliff where one, people can't reach it, and two, it's hidden from on top, so it's more difficult to find. So ISD fits within a range of risk management strategies. So we've got inherent, which means we eliminate or minimize a hazard. We've got passive, where we use an engineered safeguard, but it's a safeguard that doesn't require any input of energy. We've got active, where we have another safeguard, but it requires energy going into it, like electricity or pneumatic air. And we've got procedural, which is where you manage your hazards by practices rather than engineering. Thing about inherent and passive is that sometimes the line between them can get kind of blurry. So for instance, suppose you rate a pressure vessel, your operating pressure is 10 bar and you rate it for 50 bar. That's a passive protection measure, but it's also inherently safer design. That distinction doesn't really matter as long as it's there. So you'll notice in the name it says inherently safer and not inherent safety. And that's because ISD is only safer relative to something else. So nothing can be inherently safe because your process will always have hazards in it. It's impossible to engineer out hazards. So an inherently safer design option is only safer with respect to some other kind of hazard. An example of that was chlorofluorocarbons. You know, those bad stuff, those poking holes in the ozone layer. So back in the early 1900s, CFCs were actually the inherently safer option. When you're dealing with refrigerants like ammonia, which is flammable and toxic, or sulfur dioxide, which is toxic, or light hydrocarbons, CFCs look a whole lot safer. But with ISD, you have to be aware that modification of one control can remove a hazard or control a hazard, but it can also introduce other hazards, which you may not expect. Within that range of risk management strategies, your inherent and your passive strategies are really what you want to be going for because they're least likely to fail. Benefits of inherently safer design. So fewer inherent hazards. Your hazards have been identified, assessed, understood, and controlled. You've identified your opportunities to control your hazards, and your likelihood has been reduced. Improved capital investment. So the less stuff you have in a plant is the cheaper it is to buy the plant, cheaper it is to operate the plant, cheaper it is to maintain the plant. It also allows you to have a practical risk management strategy because the less things you have to go wrong, the simpler your protections, the less complex your risk management strategy is, and it's overall easier to deal with. So ISD is based around 4 principles. Minimize, which is just, you got to use your hazardous substance because that's what you need for your process, but you just use less of it. Substitution, which is where you take a hazardous substance and you replace it with a substance that is less hazardous. Moderate, which is where you use less hazardous conditions, or you use a hazardous material just in a less hazardous form. Also, you reduce the severity of your operating conditions, so you operate at less temperature, less pressure, less voltage, current, etc. Simplify, so that is self-explanatory. You simplify your process, you make it easier for somebody to operate. If it's easier to operate, fewer mistakes can happen. Okay, so minimization. So minimization is just, as I said, you have a hazardous substance and you decide I'm going to use less of it. So if I have a manufacturing plant, I want to reduce the inventory of any hazardous substance that I have on my site. That's not just raw materials or final product. You also want to reduce your intermediate storage, so pressure vessels, reactors. Can anyone tell me another area where you can minimize the volume of hazardous materials that you have on site, besides tanks and vessels? Piping, right? Use smaller piping if you can, because a significant volume of stored inventory on site is going to be in your pipework. Okay, so as an example, this was a bourbon distillery in Kentucky. So on November 7th, 1996, lightning struck one cask warehouse. That warehouse went up. High winds carried the fire to other cask warehouses. There were 20,000 barrels of bourbon in each warehouse. So these warehouses were destroyed. A whole lot of bourbon ended up in a nearby waterway, causing environmental pollution. So in terms of ISD considerations, you want to look at things like, can the inventory of each warehouse be reduced? Do you really need to be storing 20,000 barrels in each warehouse? Can the warehouses be constructed of fire-resistant materials? Because this was all wood. Also, can you achieve better separation or segregation between warehouses so that if one goes up, it's not spreading to a whole bunch of others? Trevor Kletz had another expression. He said that companies have no memory. And what he meant by that was that something goes wrong, the company recovers from it, and then somewhere down the road, it goes wrong again, and they haven't learned anything. So in this example, the distillery rebuilt their warehouses exactly the same. 2 years later, there was another bourbon distillery nearby that exactly the same event happened to them too. Lightning struck a warehouse, a bunch of warehouses went up, a whole lot of bourbon flowed into a nearby waterway. Okay, substitution. So substitution just means that you're taking a hazardous material and you want to replace it with something that is less hazardous. So as an example, you want to use water-based paints instead of solvent-based paints, which could be fumey, flammable, etc. If you're using solvents, you might want to use a solvent with a much higher flash point than the one you're using, so it's less likely to ignite. This was an example of a large brewery that FDT was working on, and it's an example where you can consider inherently safer design, but realistically just may not be able to implement it. So this new brewery was going to use ammonia as its refrigerant. So it had a big ammonia plant with a lot of ammonia on site. And I get why they went with it, right? That's what they're used to using. You also have that ammonia is an extremely well-known refrigerant, and it works very well, so people are more likely to use that. But some of the problems with ammonia, it's an asphyxiant, it's flammable, potentially explosive, it's toxic, can burn your eyes, burn your skin, damage your eyes, very toxic to aquatic life. But one of the things is, in this design process, at no point was it ever asked, can we use anything other than ammonia? All right, and even if we have to use ammonia, maybe we can use less of it. Okay, moderation. Moderation is just using a less hazardous version of a material, also using less severe operating conditions. So in terms of moderating hazards with materials, maybe you can use a more dilute version of a hazardous material. If you're dealing with liquefied gases, maybe you can refrigerate them, so they're less likely to turn into vapor. Change of physical characteristics, example, particle size. Maybe you don't want to use finer particles, which lead you down the road of dust explosions. In terms of moderating a process, you can do stuff like building stronger primary containment, choosing where to site your plant, also where to site your hazardous processes in relation to occupied structures. Materials separation and segregation, so spacing things apart or dividing things with physical barriers. Yeah. Okay, so again, same large brewery that FTT was working on. So they had a 92-degree high-pressure hot water system, and the hot water supply was at 8.5 bar. And it came up in the HAZOP, wait, why are we supplying this at 8.5 bar? Surely we don't need that pressure. So one of the recommendations from that HAZOP was to go away and look to see, can you reduce that pressure? And if you reduce that pressure, then it means that if you do have release, it's less likely to be severe. You don't have somebody being hit in the face with high pressure hot water. So other advantages of using less pressure, you can use materials of a lesser grade, and it would also lower the frequency of inspections because now you're not as concerned if your system experiences a loss of containment. Simplification is pretty straightforward. It's just making your process more user-friendly so that it's easier to operate, easier to maintain. People are less likely to make errors where bad things can happen. So examples of simplification, using stronger, higher pressure rated equipment, eliminate unnecessary or seldom used piping and valves so you don't have dead legs where you can have corrosion. You don't have valves which you're not maintaining and can leak. Using stuff like gravity flow instead of pump flow so you don't have pumps to deal with. Effective human factor design, that just means it's easier for somebody to interact with that process. Valves are easy to operate. They're not high up, they're not low down. They have all the information that they need to understand what's going on in the process. Okay, this is another example from one of FTT's projects for a tequila distillery in Mexico. So at this distillery, they use a CIP system for cleaning in place for the equipment. And the acid supply comes from an IBC. So they have hydrochloric acid, and they move an IBC from their storage to where it needs to go. The operator has to open the IBC, put in a lance, and there's concerns with forklift movements, people getting struck by the forklift, or the forklift dropping the IBC, or hitting the IBC, or when the operator pulls out the lance, getting hydrochloric acid on them. And I asked the question, well, why are you even doing it like this? Why aren't you using a fixed tank where you're filling it from the exterior of the plant and you don't have this lance, you don't have forklift movements, etc.? And the answer is that is a valid point, but it's too late to change it now. All right, so ISD can help as long as it's easy, as long as it's early enough in the process that you can actually use it to make valid changes. Okay, application of ISD. So actually applying ISD in a lot of ways isn't very difficult. It's really a change in thinking, change in design philosophy, but actually getting it right and doing it to the level that where it's useful is actually a huge pain. So if you look in industry and you ask somebody, well, let me see your company's inherently safer design procedure, you will not get one. Nowhere in the end, well, I wouldn't say nowhere, but in my experience, nobody has one. And would anyone like to take a guess as to why no company has developed inherently safe design procedures? Because nobody wants it. Nobody wants another procedure to follow, right? So your first step of applying inherently safer design, like anything else, is to have a good plan. A lot of people don't do this. It's just, let's see, somebody comes up with an idea. Oh, well, maybe we can do this better with ISD. But that's not the way it works. You actually need to dedicate some time into planning out how you're actually going to do it. So stuff that needs to go into your ISD plan, you need to identify where in your process can most benefit from ISD. So you identify the processes, the materials, the kind of hazards that you think you might encounter over the full life cycle of the plant. Not just the design, but actually through the operations and maintenance. You want to focus on identifying design options that have the lowest inherent risks. You want to set goals and criteria by which ISD achievements can be assessed. You want to identify a schedule of activities, the resources that you need, what the deliverables are going to be, for how you're going to identify and manage your hazards, as well as you want to get input from the people who will actually be using the process as part of your ISD plan, because they know what is likely to go wrong. Okay, so for hazard identification and risk assessment, you want to choose which methodology is best for the design phase that you're actually in, and you want to develop a schedule for when you're actually going to do those. You want to use consistent risk judgments across all project stages using a risk matrix and risk criteria. And you want to identify a preference for the types of risk control measures to be used. So inherent, active, passive, engineered, procedural. And the reason why you do that is realistically, you can't control everything in your process with inherently safer design. You're going to have to make decisions where you're actually going to have to use engineered safeguards or procedures. Conflicts. So as I said before, an ISD option is only safer relative to something else. And when you're doing your design, you're going to have to make choices as to where you're going to put that ISD priority. Like with CFCs, the priority is a safer refrigerant that isn't going to set your plant on fire, but it's also going to destroy the ozone layer. So which one is the bigger priority for you as an operator? So in managing conflicts, that's not going to be easy. There are mathematical methods for deciding how to manage conflict, and I am not going to go into all of those because I suck at math. But it's there. It's when you're trying to decide on how you're going to implement ISD, you need to decide how you're going to manage the conflicts that come up when you're actually going to do that. Measuring how well ISD has been incorporated into your project. Again, there are mathematical indices that are geared towards that. Caveat, none of that has been formalized. It's only been done at a research level. So if you're going to use one of these or several of these, just be aware that they're not fully fleshed out yet. Okay, so within the life cycle of a project, you're going to be applying ISD at all your stages, and how that gets applied is going to look different from stage to stage. So at the very beginning, like concept, you're going to be looking at basic process technology, what materials are going to use, what your byproducts are going to be, what your waste products are going to be, how your system is going to be routed, where on the sites things are likely to be, and how things are going to flow around the site. In feed, you start getting a lot more information about what your process is going to look like, so you can start applying ISD in more detail. So location of manufacturing facilities, size and number of production lines, process control philosophy, selection of specific types of equipment. In detailed design, you're starting to actually design your process now. So you're looking at sizing of your equipment, pressure rating, what the actual inventory is going to be, where stuff is actually going to be on site, how operators are going to interact with your process. In operations, you want to look at how people are going to be interacting with the process. Is there room for improvement? How you're going to develop your operating procedures and make sure that they're actually useful for an operator. Okay, these are 6 steps on how you can implement ISD. That's a lot of steps, which is maybe why people don't use them. So quite often, as an engineer, engineers like to engineer things. So their risk management thought process looks like, number 1, can the hazard be eliminated from the process? And if it can't, jump straight to step number 5, and you start engineering stuff. All right? That's not the way ISD works. So if your hazard can be eliminated from the process, you do it. If you can't, you move on to the next step. Well, can the magnitude of the hazard be reduced? Do alternative designs identified from questions 1 or 2 increase the magnitude of existing hazards? So maybe you've been going well, and then you hit step 3, and then you realize, well, wait a minute, I've kind of gone off track here. I'm actually getting hazards, which I didn't think about before. Step 4, if you end up with more hazards, you try to understand those hazards. You identify passive, active, and procedural safeguards to manage your hazards. And you use a logical decision process to select an optimal design. ISD approaches. So this is where it gets really interesting. Right, so you can implement ISD formally in like 3 different ways, right? So the methods are a checklist, process hazard analysis, independent process analysis, and integral to process hazard analysis. So when you're implementing ISD, you're looking for orders of protection. So in decreasing priority, ideally you want a first order ISD. If you can't get a first order ISD, you want to get a second order ISD. If you can't get a second order, then you go to layers of protection. What that actually means, as an example, is say you're a fiend for barbecuing. You absolutely love to barbecue. Day, night, you're barbecuing, right? But your concern is a gas fire. So you decide, okay, you know what? I'm going to do away with my LPG grill. I'm going to buy an electric grill, right? That removes the gas fire hazard. But maybe your thing is, okay, I really like using LPG to barbecue. And I do it so often that I have 30 cylinders of LPG in my garage. Maybe that's not a good idea. So I'll make the sacrifice and I'll drop it down to 5. Okay, that's a second order ISD. But then you think to yourself, okay, I really like to barbecue. I really need those 30 cylinders of LPG. So what I'm actually going to do, I'm going to buy the plot of land across the street. I'm going to build a reinforced concrete munitions bunker with CCTV and fire protection. I will keep all my LPG cylinders in there. That's your layer of protection. So checklist PHA is probably the simplest way to incorporate ISD. So what you're doing here is you make a checklist beforehand where you write down where you think you're going to get hazard in your system, what those hazards are likely to be. And then you get everybody in a room and you go down that checklist and you evaluate each hazard. And coming out of that, you come out with a recommendation on how you can improve things, right? So the advantage of that is it's really simple. The disadvantage of that is that you've already limited yourself by using a checklist. People come into the analysis and they see a checklist and they think that is the scope of the analysis, but people need to think beyond what's documented in the checklist. Independent PHA, so it's like any other PHA you may encounter, but you're only looking at opportunities for inherently safer design. So in a normal HAZOP, for instance, your recommendations would probably be around engineered safeguards. But in the independent PHA, you only recommend things that apply to inherently safer design. Disadvantage of this method is that it's more heavily PHA based, and you may not have a team that's experienced in PHA, and they're going to have to learn how to do this properly. Also, the other disadvantage of this is that it's one more PHA that you're going to have to do in your design, and that's probably not going to sit well with your project manager. Integral to PHA is where you take a regular PHA like a HAZOP, and you do it like a regular HAZOP, but you incorporate ISD opportunities into it. Disadvantage is that it's going to make your hazard longer, and that's not going to be popular in your design project. Okay, so to summarize, ISD is a philosophy which focuses on elimination of hazards or reducing the magnitude of hazards. You're not going to be able to make a process 100% safe with respect to all possible hazards. Inherent and passive approaches are the most reliable, but your risk management plan is going to have to incorporate all of the different types of risk management strategies into it. Very importantly, if you're making the decision to actually use ISD, you're gonna have to document it. That's not gonna be a small amount of documentation. It's going to be a lot of documentation. It's not going to be popular, but if you're committing to do it, you commit to do it right. To close off, using an example of where ISD was done right. If you're familiar with the Apollo capsule, back in the 1960s, when they were looking at how to decelerate the capsule splashdown, one of the options that was floated was a pop-out rotor blade system, which would have been awesome as hell. But realistically, doing that with 1960s technology probably wasn't going to work. So they went over to a system that used 3 main parachutes. And that worked well enough that it's pretty much standard for Western design capsules up to this point. Last year in the news, there was one particular company's space capsule that left their astronauts stranded on the International Space Station for 8 months. Back in 2019, that capsule was going through a launch abort test, which is where you put the capsule on a pad, you fire the launch abort motors, and you blast it up several thousand feet into the sky, and the parachutes deploy, and it comes down to the Earth. In that test, one of the parachutes actually failed, but because it had been designed with redundancy, where it could safely land on 2 parachutes, it was actually a successful completion of the test. Okay, if by some chance you want to know more about ISD or anything else related to process safety, you can contact me, or you can contact my boss in the second row there, Dara Boone. Okay, now's your time to give it to me.
Well, thank you very much, Graeme, for a really interesting talk. So if anybody has any questions, are there any particular industries that are applying this technology?
The answer to that is no. All industries, all companies know about it. So I'll give an example. A company that I did work for, they had an ISD standard where it essentially just said you have to incorporate ISD into your projects, and we're going to be checking this when we audit your project. And they didn't give any kind of indication on how to actually do it. So what would happen is that you would run through a full project, and then some guy at the end of the project would ask the question, well, how was ISD incorporated into this project? And it's, right? So I had to come up with a boilerplate answer. We did process hazard analysis where ISD was considered, et cetera, et cetera. But realistically, nobody is applying it formally, which is the big issue. It's all ad hoc when somebody thinks, okay, maybe we can do this better. But
do you see continuous processing as a way of reducing hazards, say, in the pharmaceutical industry? I know some companies have moved to continuous hydrogenations with a view to having lower inventories. Or
yeah, so with continuous process, you remove a lot of the operator error from it, with like batch operations. So ideally, you can automate when you can, but automation takes money, especially if you're connecting existing process to a new process, getting those talking. It's all extra resources. So it can help, but whether people want to spend the money for it, not all the time.
I believe Eli Lilly have started hydrogenations, and part of the idea was to reduce the inventory of hydrogen at any given time as well. As a former Union Carbide employee, and it's 40 years since Bhopal, when clearly wasn't inherently safe storing the material. Do you see any parallels with quality assurance and the whole quality management, Deming management, things like that? A lot of that is about eliminating the possibility of errors, both procedurally and technically.
With a simpler plant, you have more control over your process. You have less downtime. You have less things that can go wrong, and all of that contributes to the final quality of your product.
Yes, Michael J. Yeah.
Is there any of the indices or metrics that you mentioned that can put some kind of dollar value on implementing?
The index wouldn't do that. With your conflict management, where you look at probably cost-benefit analysis, that can give you the dollars and cents of which path you need to go down.
But that's not conclusive or convincing.
No, it's not going to measure the final output of how inherently safer your plant is, but it can steer you down the right roads at least.
Graeme, thanks very much for your presentation. We've got some pioneers here in the audience, and they're starting off on their design project at the moment, and they're looking at different process routes for their assigned product. Have you any advice for them in terms of how they could do kind of a smaller implementation, let's say, of what you covered there this evening?
Get started early. That's the ideal. That's the ideal way. But a less formal way is to at least document your decisions. So when you're deciding what equipment to use, what materials you're going to use, at least when you have a bunch of people making decisions, document the decision that was made and what got you to that decision. And where you can, do a hazard analysis on it. That would at least tell you whether you're going right or wrong.
Online question there, yeah. So, Graeme, in the food and beverage industry, what are some key examples of inherently safe design practices that help prevent contamination or ensure equipment safety?
Okay, a good example would be you normally have compression at your brewery, like say in your refrigeration system. So with your compressor, you use oil-free lubrication, so you don't get oil being carried over into the downstream process. Another way is you're using stuff like glycol in heat exchangers. So there are food safe options that you can use in case you get a crack in a heat exchanger, so you're not contaminating your product.
Very good. When you mentioned Trinidad and Tobago, I remember the president in 2009 was a chemical engineer, the president of Trinidad and Tobago. He came to the World Congress of Engineering, so it's one of for Trinidad and Tobago, along with the current president of China, but that's and the Pope. But we remember that. And I remember as well, one of the biggest industrial accidents in Ireland was a fire in the distillery in the 1800s. And a large number of people died because the whiskey went down the street. People took off their shoes, scooped up the neat whiskey, and died from alcohol poisoning. So, an unusual hazard there. Any more questions? Anybody? Any further? Yes. Yeah.
One question. I love the concept of simplification and inherently safer design. Do you find that engineers today or safety professionals today prefer automation and layers of instruments rather than just inherently safer, simpler design? And how would you argue with against the over automation, over digitization of an unsimple design?
That's an argument that's going to be tough to win. With inherently safer design, because it's a design philosophy, what you really need is buy-in from the people at the top of the company that say, this is how we're going to do it. You have to incorporate this formally. It's only with that kind of backup where you can say, let's at least consider doing it this way instead of the other way. So for the final year people, if you're going into into like engineering companies, make good friends with the process safety subject matter experts at your client companies, because at least that way, when a project manager wants to use something that you think you can do better, you can run to that person and say, hey, I'd like to do it like this, and chances are they're going to agree with you, and they have the weight to change the direction.
The question. So, what criteria would you recommend using to ensure you apply inherently safer design for process route selection at the early stages of a project?
So for one thing, where those routes are going to be run. So you've purchased the site, you know the shape of the site, you have a rough idea where you're going to be putting things. So you want to start looking at separation and segregation of your occupied structures and your hazardous process. You also want to look at the routing where you can have catastrophic failures of equipment, which can take out process piping and make your situation worse. You also want to look at the flip side of that, where you're looking at how you're going to route, like, say, your fire water system. So if you have a catastrophic failure, you're not taking out your fire water piping as well. You also want to look at the materials that you're looking at for your routes. Are they sufficient for the operating conditions that you're going to have? Is there anything on the site, like is it near an ocean? So maybe corrosion is more a factor, so you'd have to change grade of your piping.
Very good. And Pat Kenslas, if ammonia and CFC are problems for refrigerant gases, what would you recommend as a safer option?
So I'm not a refrigeration expert, but refrigeration is a big area. So there is a lot of research into refrigerants, and safer refrigerants are being developed. But one of the problems is that they're just not as efficient as the really bad stuff. But work is being done.
Okay. And how expensive is it to introduce ISD?
Depending on your process, it's probably going to be expensive, and it's not the engineering that's going to be expensive, it's the additional work and effort that you're going to have to put in to actually making your design. So where you're used to, say, you're getting all the engineers into a room and you have a problem and you work out that problem, and then everybody goes away. Now you're going to have to document everything that goes into that process, everything that comes out of that process. You're going to have to do intermediate hazard analysis on the decisions that you make. So yeah, it's going to be a lot of documentation and resource costs.
Further questions here?
Are you seeing much more? A lot of the work seems to be on the inherently safe plant design, as opposed to the process coming down.
Yeah, definitely. I mean,
we talked about it a decade or 2 weeks, and has the pendulum switched in terms of, you think the processes are, whether that's materials in the process or the actual process conditions, simplified?
No. So I'm that annoying person where you ask me to sit in on a hazard analysis, and my first question is going to ask is, why are you doing it like this? And it's really it's what people are used to doing. That's what they know. Within the food and beverage industry, everything is on a time crunch, so you do what you know. And by the time it gets to me, where I could say, well, maybe you can use an ISD approach on this, it's too late to change it. So.
Just one thought, we've been talking about ISD during design. One of the issues that we find sometimes is that automation systems, they grow and they get more complicated, and you talked about simplifying them, and there is a space in that place, in that area, where you need to go in and start pruning. Do you see ISD be used for pruning of pipes and dead legs and obsolete equipment, or is there an area for that?
Yes, but it's ad hoc.
Mm-hmm.
It's really only when someone asks about dead legs in a HAZOP, for instance, then people start thinking about dead legs. Well, like I'm involved in a HAZOP at the moment, looking at a filtration system. And I looked at these PNIDs, and they are just sample valves, just all over the place. There's probably like a dozen sample valves in one section of the process. And, you know, I asked about it and they said, well, you know, we needed to evaluate stuff, but they're all potential leak sources that are coming up in the HAZOP. So the question is, do you really need that many sample valves?
So I have one comment, Brian Cott. If you think process safety is expensive, try having an accident. So, and I suppose my question on that is there any push from insurance companies to in the direction of ISD?
I don't know about insurance companies, but like in the US, the National Fire Protection Association, and this is specific for the beverage industry, where they're starting to lose sleep on the distilleries and breweries that are being built in the US, where they've identified serious problems with these facilities, but there's no legal push to actually do it better. So people are trying. I'm sure the insurance companies are trying too. But there's only so much you can do.
Yep.
IC seems fairly like a non-brainer really. General design. You were saying that companies don't really have implementation of an IC now, or you also saying that there's a lot of paperwork. Is there not like a middle ground that we can sort of simplify the process of ISD but implement it as well, so there's not that money spent on paperwork and time spent?
There isn't. It's kind of like a HAZOP, where once you invoke the gods of HAZOP and you say you're going to do a HAZOP, you're fully committed, and the only way you get it done right is to commit to the process and go through the process rigorously. So with ISD, it's just the nature of the beast, which is why nobody does it.
So I suppose, sorry, the question was basically, is there a cheaper, more shortcut method? And as you've heard, basically the answer is no. Yeah. So sorry, that's for people at home. Any further questions? Yes.
Just in terms of plant maintenance, Graeme, is ISD process that can be applied when you design the plant to consider maintenance? Because that can be quite a hazard.
Yep, because with ISD, the less stuff you have to maintain is the easier your maintenance. But also within the ISD process, human factors comes up, and human factors will influence how you do your maintenance. So another company that I worked with had a knack for putting isolation valves behind equipment where nobody can actually access them. So those are the kind of considerations that you would come up with your ISD when you're looking at making your plant simpler to operate and maintain.
Okay, and one last one. Kieran Kelleher, are there any industrial forums where companies collaborate and develop a harmonized approach and lessons sharing effort in relation to ISD?
Not that I'm aware of. And I would think that's not really done because nobody's doing it formally, and nobody can say, okay, here, ladies and gentlemen, here's my system and I'm doing it really well.
Okay, we now wrap up the questions, and if anybody has further questions, they can ask Graeme afterwards.